Hi everyone, this is the fourth and last video for chapter 4, so for section 4.2, 4.3. So we just kind of have some last minute little notes of things to point out. So in this example, we want to decide whether or not x plus y to the nth power is the same thing as x to the n plus y to the n. So listen to the way that I said that. We want to decide whether or not x plus y to the n is the same thing as x to the n plus y to the n. So how did I say this one? So whenever we're kind of talking math out loud, we use pauses to express what we mean. So I said this as x plus y, and then had a little pause there that said to the nth power. And that pause helps us denote these parentheses. So I paused after x plus y to kind of indicate that we do that first. That is the first thing we do is do x plus y, and then we raise it to the nth power to help denote those parentheses verbally. So that's just one little note about how to talk math out loud to people. It can get really complicated, right? Even this x plus y to the n can be complicated versus, right, if I didn't have that pause, you might think that I was saying x plus y to the n, and those are different. Okay, so we want to decide whether or not this is a true statement and explain why or why not. Okay, so let's just kind of think about this using our basic properties and rules that we have. So what does x plus y to the n really mean? Well, this is multiplying together n copies of x plus y, right? That's what the definition of exponents tells us. Then we have n factors or n copies here. So that's n copies, but x to the n plus y to the n is what? So we take x multiplied by itself n times, and we add it to y multiplied to itself n times. So again, oops, that one. Wow, this is kind of hard to write today. There we go. So these both have n factors. Okay, so right, by the definition, you can see that these don't represent the same thing. But if you can't see it from here, let's take an example. So this is not true. And when something is not true, all you need to do is find an example of where it fails. Right? It doesn't, we're trying to show that this is true generally. And so to show that something isn't true generally, you can show an example of where it fails. Remember, we talked about this before, that to show something is true in general, you cannot just use an example, but to show something is false, you can use an example. So let's just look at n equals 2. So at n equals 2, x plus y to the n is x plus y squared, which is x plus y by the definition times x plus y. Okay, so right at this point, you might think to use FOILing, but I want to show you a different method. So we want to do this distribution here. So we want to distribute the x to the x plus y and the y to the x plus y. And then we get x squared plus xy plus xy plus y squared. And this second xy comes from the commutative property. So this is x squared plus 2xy plus y squared. Okay, this is not the same thing as x squared plus y squared. You can clearly see why, right? There's this 2xy that comes in from our distribution. And for that reason, these are not the same. So you can see that kind of looking up here. Whenever we have these factors, we're going to have all of these middle summands that aren't x to the n and y to the n that come in the middle here, but with x to the n plus y to the n, that's not the case. So although, right, a lot of times math works really nicely, we cannot distribute exponents, right? So it might be, you might want to think that we can put this exponent on each of our variables, but this is not correct, right? We just showed why you cannot distribute exponents is because you won't end up with the same thing. Okay, so for this next example, this last example down here, we want to write an expression for the area of the shaded rectangle evaluated when a equals 6 using two different methods. Okay, so based on this picture, we can see that the area is length times width. So the area is going to be 8 times 14 minus a, right? The length times the width. So first, we want to use the order of operations. So if we use order of operations first, we're looking at 8 times 14 minus a, which is whenever we substituted 8 times 14 minus 6, right? Because we're doing it when a equals 6, which is 8, and we do the parentheses first. So this is 8, and then this just gives us 64. Okay, so that's doing this using the order of operations. So now we want to do it using the distributive property. So we start out with 8 times 14 minus a. 8 times 14 minus a. And then what we do is we distribute the 8. So this is now 8 times 14 minus 8 times a. 8 times 14 is 112 minus 8 times a. And now that we've done the distributive property, now we want to substitute a equals 6. So this is 112 minus 8 times 6, which is 112, minus 48, which is indeed 64. So these both gave us the same answer. And this may seem kind of odd to you because our order of operations tells us we need to subtract first. But this is kind of one interesting thing to point out is, although we have this order of operations that tells us this is the standard way of doing things, there's a way around it. If you really don't like doing it that way, we have this distributive property that lets us do, right, distribute the multiplication, and then we can multiply first. So this is just kind of an interesting thing to point out, that this distributive property can kind of override the order of operations in a way, because, right, the order of operations would said, well, subtractions in parentheses, subtract first. But if you have this tool of the distributive property, you can say, no, I want to multiply first, and then it'll all actually be correct. So right, that's one thing that's nice about math, is we have these tools that let you kind of override things but still be correct. Okay, that's all for this worksheet, and that's all for this video.